Well, okay. Yeah, okay. Okay, good evening, good afternoon, class. And anybody else want this recording turned on? It's okay with me. Okay. So what we're gonna do is all right. So what we're going to let me see the sound volume. Is it okay? It looks okay. All right, class, this is the last day I'm going to spend on GDB. There's a couple reasons why it's useful. One is it can be used outside of this class. GDB can be used, like the example today is mostly C++. GDB can be used outside of assembly programming. In fact, that's its more common usage. Second is, I had a reason. Oh, from GDB, we can discover the architecture of memory, the structures that are there. And in the next 45 minutes, that's what I'm going to do. We can discover how memory is really organized more than just me. I can draw you diagrams taken from a book, but that doesn't quite tell it like seeing it real. Okay. So GDB, you can use it someplace else, and you can learn about how the structure of memory is. And third one is it's on the final test. Okay. So there's three reasons why to know about GDB. And then we got to go on to other things after today. I have a program. We're going to start on that first, I think. Um, and well, how can I want to keep the chat messages visible. Okay, I'm going to share the screen and we're going to do it right here. Okay, I think you see the whole screen. Why did stuff jump around? Okay, I have a program that contains three files and they're all kind of junk programs. They weren't created to do anything specifically. They were created just to help us learn about GDB. Okay, so can I find them? I think I have all three of them here. Is that there's the one that says main. And if you look, it's just a bunch of numbers declared. And here's declaring a pointer to 6.0. Here's declaring an array called E1 with some numbers in it. So all of this is just kind of like useless declared stuff, but that's okay. What we're going to observe mostly is in the middle right here, it calls another function whose name is M1. Okay. Okay. And then I have a screen here. Is this M? That's not M1. Okay, we'll find it here. Here it is. This is M1, and it looks like the first one. A bunch of numbers declared, more numbers declared. And that's a tricky way how to show, see this variable H2 up above. Uh, showing it in decimal is easy, but showing that value in hex takes a little bit of work here. It's not terribly important. We may talk about it towards the end, but nevertheless, from C++, you can show numbers in IEEE hex 64-bit form. And then the important thing is this one calls another function right here. Its function is called M2. So we have M0, M1, and M2. And M2 looks like the first ones. Declares some more numbers, and there's some float numbers it declares, but it doesn't call any more functions. Okay, so each one of those is going to make an activation record, and I'm going to focus on what those activation records do to each other, how they interact. Okay, follow along. Now I need a terminal window. Do I have one? Here it is. Okay. It's really, it looks ugly. CLE4. And let's stretch it a little more. Okay. I'll try to keep my eye on watching the chat messages often. Okay, so you notice there's 3 C++ functions here. They're dummies, but they serve the purpose of showing us activation records. So I'm going to run this shrg.sh. Okay. Now, those 3 files are full of declared variables. I don't do anything with them. So there's lots of warnings that say you have an unused variable. That's expected. Those are not errors. Those are intentional, that there'll be a lot of data declared because I wanted to see how much of that goes into an activation record. That's what it was for. Okay, but down here we have the usual welcome message from GDB, and it says it's running the program action.out. And the first thing you should do is put a break someplace. Main, let's go break space main, M-A-I, well, not uppercase, M-A-I-N. Okay, I don't know if I ever explained how do you declare a break on another file. Like here we're looking at the file, it's hard to read, but it's in the title at the top, active2 CPP. Now let's suppose I wanted a break on line 27 of the file active2.cpp. Then over here I'd say break on active2.cpp colon 27. And whoops, except I lost the focus again. Colon 27. That will put a break on line 27 on that next file that we don't see at the moment. So IB. Okay, so you see over there in the green colored font that file number 2 has a break at line 27. Okay, everybody here. So let's run this. We say R for running. And we're starting in and to walk through that first function. It says welcome. There's the welcome message. It says I'm going to assign 14 to variable A1. It did it, but there's nothing for us to see yet. Can we check that? P/D A1. Yeah, so it says that's equal to a 14. Now, if I did the same thing with, did we execute B yet? Let's execute that. If I did the same thing with B1, it's going to truncate it. P/D. Oh, maybe not. Well, let's find out. B1. No, I think I know it. Because it has no fractional part, so we're not shown that. I need a number with a fractional part. No, no. No, there's still no fractional part. There's no fraction. Okay, it's going to create a pointer to a double. No, that's fine. And it's going to create some other pointer to an integer. Okay, now it's getting ready to call. I'll try to find out how to output a float number in a moment. It's going to call the second function, the M1. But before I do that, I want to make some notes on the side here. Okay, so P/X $sign RBP. That's got this number. Let's do the same thing for RSP. And that number is a little bit less. And everything in between, including the two ends, is the current activation record. P/D parentheses $sign RSP. No, we better take the large one first. RBP minus $sign RSP parentheses divided by 8 plus 1. 27 numbers, 27 quad words in this activation record. I'm going to write it on side paper because I need to come back and use that 27 pretty soon. Okay, and you know what it looks like. P/X/27 quads X G $sign RSP. What did I miss? I missed the slash mark. There. Okay, I think you saw this. I don't know. I think you saw this last class maybe. The back end is all zeros except it has a 1, and the front end is up here, and the front end's address DE50. Here's the front end's address DE50. Here's the back end's address DF20. Here is the back end with its address. Okay, and what's one of the numbers we had, like 2.0? That should be 400 as an exponent. There's a 400 exponent, see that? And this would be, if that's a, what do we say that is? That's a 2. This is probably a 4.5, about 8, 6, it looks like. Do we have any 6? Or I can't compute in my head. Okay, 400 is 2, 401 is 4, 402 is 8. So this is the number 8, and then right after it is an 8, which has first bit is a 1. That's halfway between 8 and 16. 8 is, in fact, is in base 16 counting, it's halfway between the two. So halfway between the two is a 12. And do we have a 12 up here? Here it is. You can find B2 in our activation record. All right, well, I'm going to leave that because we have a goal here. We want to study what happens when we have 3 of these things. The next thing to execute, NI doesn't execute it, but it just shows it to us. It says you're going to call this function. So I'm going to use an S. S means you step into the function. And now we're in that function. In fact, it tells us right here that we're in the file active1 CPP executing at line 15. That's okay. Let's go one step further. Okay, now we're definitely in it. What do you think the size of the, we have a brand new activation record. What's its size? I'll go backwards to pick it up. It's that one. Oh, the size is 35. I'm going to put that on the side here. 35. All right. Now, this one in the previous function, the first function, its front end was here. And it ended with a 50. See, these numbers are getting small as you go upward, the blue ones. There, it ended with 50. And so it only makes sense that the new activation record is placed on top of the stack. It would be a lower number sitting up here somewhere. Okay. This is back end, that's the front end. The new activation record goes to the front end. So let's go make it happen. Piece, no, it's got to be an X. X slash 35. So I want to use slightly more. Let's use 38. And X and G and $sign RSP. Okay. So, wow. Here's the back end down here. Did that go right in the, look at its address, DE50. Did that go? You know what? I actually asked for more than that was necessary. You gotta find the back end. P slash decimal P slash X $sign RBP. Oh yeah. The true back end is at DE40. I asked for 3 extras when I said 38. But here is the real back end. Okay. And the front end goes all the way to here. And so the front end address is DD30. How does that relate to our previous one? Something mysterious. We're missing a quad word. Okay. No, it's out here. It's in this area. Here's from high end, high addresses going all the way through this. You go, the addresses get lower, and there's was previously the front end of that activation record. And then further down in lower addresses yet comes this one, DE50. Oh, no. I said it wrong. Now it's clear. This yellow part is our old activation record. It ended on DE50, but this one resumed. Remember, this is extra stuff. It resumed on 40 and continued on down through the whole stack. Well, it's too confusing to see it in separate halves. I'm going to put them together. 35 plus 27 is 42, 52, 62. We'll use 64. Okay, so P X slash 64 X G $sign RSP. Okay. Now, well, we have 2 activation records here at one time. Where the old back end? Here it was at DF20. There it is, DF20. That's the old one, 00001. And then we had How far did that go? It went to DE50. DE50. Yeah, it went to here. Okay. And notice it was on the boundary, both front and back, while that was alive. And then the new guy started here because the back end is automatically always on the boundary, ends in a 0. The new activation record is here and going up in the up direction. Who got in the way? This one. So in numbering sequence, we're counting down in addresses. This was, did I put it in the right place? This one. This was the old front. Then there was a number inserted, and this is the start of the new back. Old front attaches right next to the old back, except for this guy's in the middle. Okay, so you know who that is that's stuck in the middle? Okay, that's RIP at the time of the call. So now the activation record goes to here. And that RIP, where my cursor is moving back and forth, that is the final quad word of the old activation record. And then the new one starts over here. And it continues into lower addresses from number 40, address 40, up to, well, I think it's all the way to here. That's the new activation record. Okay. Still with me? Okay, there's something mysterious happens here. The yellow part that you see is the new activation record. It has a front and it has a back. The back is where my cursor is. The front is up at the top of the page. What is in the back end's first slot? The new activation record, the back end's first quad word. And I'll outline it. It's right here. Anybody know what that is? You got to guess the data structure here. It's telling you something. What does that number represent? You can't see it? Somebody guess. It's some zeros, 7FFFFF, DF20. That's very special. Oh, you got to be better than that 11 o'clock class this morning. They guessed it really quick. Is it address or is it data that's stored there? Have you read last semester's final exam that's posted? That was a question on it. So, okay, you have to find, it's not data. Data would be like a 2 or a 5 or a 400. No, that's an address. So the address goes to where? Goes to here. And so the first quad word of the activation record is the address of the old activation record's first quad word. So that's the address of him. And this one back end doesn't have a previous activation record that it can put an address there. So it puts in zeros and a one as filler data, as a way of zeroing out. Okay, so put that down in your notes. It's going to show up on the test. Okay, that's the back. That's main. Main doesn't have a predecessor, so it ends up with 0, 1. And the successor ends up with the address of main, which is over here. Okay. All right, we're gonna go back to where are we executing now? Okay, so next we're about ready to print the welcome message. Okay, so next, and it made the welcome message. Then it's going to print two numbers, and it did. You know, it outputted a 2 and a 12, and then it created a long integer. Oops, too many n's. And it created a -2, and it's setting up another message. I was going to print that other message, and it did. It says that 100 in 2's complement equals 64, and 2's complement hex -2 is equal to FE. That's so good. And so here's another one. And here's another one, and another one. And then it's, oh, the trick was to show, okay, that this, if you're recording it, you gotta save it. H2 being equal to 64, that's not 2's complement. That's IEEE form. Okay, so I want to be able to output H2 equals 64 and then equals to a IEEE number. It has two forms of output. The decimal one you're looking at in green, and then the IEEE one. I think that comes next. Yeah, it takes some setup. Okay, and a static cast. And so here we're getting ready to format it. H2 is equal to a decimal floating number and a hex number in IEEE format. LX is for long hex. So let's continue to the next one. And then it says we're going to print this thing, and then there it did it. That was the goal. The hard one is to get this one to appear from C++. This one comes pretty easily. You just format it with LF format. But this one, the hex one, requires a pointer. Those letters mean pointer too long. And then it appears, as you can see. Okay, let's go on. We're here to study memory. There's some more stuff. Now it's ready to call the next function. All right, so I don't want to use n. I want to see the next function happen. So I have to use an s. And it starts out by saying we're going to output a message. Let's do that. And the printf is going to output the message. Welcome to Amazing. It did that. Okay, and I'm going to pause here because now we have 3 activation records. Let's find out what this one is. P/D parentheses $, where's the $, RBP P minus $RSP, well, it's divided by 8 plus 1. It has 29. And I wrote them down. The first activation record had 27 quad words. The second one had 35. And now this one has 29 quad words. I'm going to put that down. M2 is 29 quad words. And if I add all those together, it is 23, 2 to carry, 4, 6, 93. Looks like 93 altogether. I'll probably use 96 to show it. Okay, so this, here it comes. This is the big one. X slash, that's not a slash, slash 96. This is the combined total of all those previous 96 X G $ RSP. Except what happened here? Lost. I want to stretch this. Can I? Something's bothering me. Okay, I can't get a hold of it. Now we can get a hold of it. Okay, now $. There it did this again. Okay, $. RSP. That looks pretty good. Okay, and C. Okay, so down here, high addresses are lower down on the page. Okay, you recognize DF20, and that's the back end of main. It has that 01. And then we go inside here and we find DF20. This address is right here. That starts the second activation record, and here's RIP. Okay, this is the second activation record, and it has address DE40. So we go in here and look for DE40. Oh, I see. It's here. Okay. That is the back end of the third activation record. And that activation record goes all the way up to the front end of itself. That would be 29 quad words in there. Okay, so the mystery guy is, I gotta find him again. I have to find him from looking at this back end, DF20. DF20. It's right here. Okay. That marks the new activation record. The old one ends up over here. This is the last of the old one, and it's off the boundary. Its address would be DE48. See, DE40 belongs to him. Is it DE58? I guess you, however you, yeah, it'd have to be one higher. It'd be 48. This is at 40 in green, and so this is one higher of 48. And it's, so the old activation record closes itself off the boundary by adding in RIP. Okay, so then this one continues up to, we have to look for a 40, DE40. There it is. It goes all the way to here. Okay, and the activation record in the middle put in this hidden guy without us knowing it. It inserted that at the time the next function was called. It's not, and it closes the activation record. That's its last quad word is that one. It closes itself off the boundary. The new guy starts. And he starts by putting the address of the previous activations back in. Oh, that DE40 came from here. That was the back DE, yeah. Did I say that right? Yeah, that was the back end of the previous activation record, and here's the RIP squeezed in, and RIP in green there is the last element of the activation record of the first function. You make all that sense out of it? Okay. And currently, as it's running, this is the front end of the current activation record that's active. Okay, so okay, we got to answer this question. I watch this. Let's see if I can make it. I'm temporarily going to stop the share. We'll go back to that in a moment. And I'm going to do the camera here. Okay, so that's like most assembly programmers, we think in terms of right to left. This one, okay, that's the block. That's the old assembly. That's the old activation record of the first function. And it had up here 000000001. Okay, and the address of that was DF20. DF20. And of course, there's a lot of data down here. Okay, the next one. Let me look up where it was. DF20. Okay. DF20. It started at DE40. DE40. Okay. And what was stored here is DF20. Okay, then we had the third one in this example was over here. Okay, I'll look it up right now. It was DE40. Okay, gotta find DE40. I'll come back to it here. Yeah, it's at DD20. DD20. And stored in DD20 is DE40. I'll show it to you live in the screen for a moment, in just a moment. DE40. Okay, and stored in. Did I calculate it with the GDB? I'll show it to you live in just a moment. I'm gonna find what value is in. What value is in RBP? P/X $ RBP. Okay, it says, my screen says DD20. So RBP DD20. Okay, is that readable? What out of 131 course does this remind you of? That was also a test question one semester. When you see those numbers, here's DF20. DF20 is in here. DE40. DE40 is in here. Its location is DD2020. And DD20 is in here. So what does that tell you? You all took 131, didn't you? Okay, suppose I draw it in a different way. You put this here, and I'll leave out the numbers. So now what is it? Nobody knows. Well, that's a linked list of pointers. List made of pointers. And that's the data structure some scientists before us decided to use to manage memory when a program is running. Those records, they're actually blocks of data, but those records are connected together, starting at the newest first and going to the next older, and then the very oldest. And the very oldest one has the null pointer inside of its first quad word. The others in their first quad word have pointer to the one that comes after them. Actually, in time-wise, we should say the one that came before. And then this one points to the one that came before it. And then RBP points to the one that's newest at all times. Okay, I think we're about, that is the, okay, let's go back where I lost my place. Okay, screen share. Okay, well, that's the key feature of the lesson about pointer stuff, that the memory is full of it, and we can get some other small facts are that the address, I'll put it in a different color, the addresses of the back end are always on the boundary, whether it's an active record or a dormant one. That address is always on the boundary. You can tell by looking at the 0 on the end of it. And this is always on the boundary. But the front end is off the boundary when it's active. So the front end will be, the address down here will end in an 8 if that function corresponding is an active function. This will be off, and this will be off, OFF, until the moment it gets called, and then the extra quad word is added in, and that's RIP. I'll just write RIP here. And that, let me rephrase that last one. Okay. When it's gone dormant, it will be off the boundary because RIP goes on to the front end and it pushes it off. When this one becomes dormant, RIP enters here and it becomes off the boundary. If this one is active, then RIP is not there. And then it is on the boundary while it's active. If it calls another function, then it's off the boundary and it gets an RIP here. Only if it calls some other function. If it never calls another function, then RIP never appears at the front end of the corresponding activation record. Okay. Well, how are we doing on time? That was, we need to do a little bit about changing values. Okay, so let's do it right now. That's the story behind memory management. Check it out on video after class goes by. Let's do. We need to be able to change values, and we haven't done that before, not very much anyway. Okay, so when you change a value of, oh, okay, you're listening, but I got to do it on the screen. Okay, let's do it here. What well, actually I should, we're in function M2. Can I show that here? This is which one? No, this is not it. How about here? Is this M2? No, that's main. Is this M2? Yes, this is M2. It's the name is right there. So we have some variables. How about let's take P1 and we'll see. Next I, has this been executed? It's doing the O's. So next and O3 and P1. P1 has been executed. So let's look at how we can handle it. If we do, okay. Unfortunately, P1 ends in a 0. It has no fractional part. So all we're going to see is the integer part, P1. See, it says the value is 4. All right, so how can we change the value of it? It would look like set P1 equal to, how about 4.5? And I think, I can't remember. I think it's supposed to be no spacing, but I'll take it out anyway. Okay, now let's see. P/X, P1, what are you? It still truncates it. Okay. Oh, we had this problem before. How do you show? How do you show P1 as a float number? Oh, well, it should be easy. P/F, P1. That's in base 10. I wanted it in decimal, in IEEE form. I might not be able to do this. Oh, maybe it's X/1 XG address of P1. That can't be right. No. This over here. 4.5 is not this ugly mess. That's not it. What if it did that just with P1? I don't think that's it either. No, that's definitely not it. Well, okay. I don't know for the moment. I'm not making it up. I don't know. Let's I'll put it on the list of things I need to look up. P show float number in IEEE form. All right, but you see how to change a value in that variable. Let's see what else is being executed. There's a negative. So we discovered that P/F P3. Well, there's that can't be right either. P/F. Oh, I think I know why. That hasn't executed yet. Let's execute it, and now I'll do that same one. -2. And because it ends in .0, it truncates the trailing part. So don't forget, line 27 up above says this will be executed next. But I'm trying to look at what's stored there. And of course, I pick up electronic garbage, starting with 4.5, and then actually execute that and create the P3 variable. And then it tells you you have -2 at that place. Okay. Next, printing messages. That's okay. That's okay. And this one's going to return soon. And here it comes next. And it's back in the caller program. In the green ink, it says this is active one, number 1. And that's correct. Okay, so we need to change other things. How about changing our ordinary register? That would look like set, well, let's look at it first. P/decimal $sign R15. It has that ugly number stored in it right now. P/X $sign R15. There's the hex equivalent. How come I couldn't do that earlier? Oh, that was with a program variable. I could never show the program variable in its hex form, but showing a register is easy. Okay, so let's change its value. Set $sign R15 equal to 102.75. Okay, so then we ask, what does it look like? Now it truncated to 75. That's not good. Why? Well, maybe it's going to truncate. Decimal is asking for integers. Okay, we have to do this as P/F $sign R15. And that isn't it either. What do we got here? R15 is 102. Now, this number that it came up with is definitely way off. That's not even close. Wow, I'm stumped. I don't know what to do with that. R15. Well, let's do this. P/X $sign R15. Not good either. 66. That sounds like that's 102, 102 in decimal. It's I can't explain it right now. It's truncating the fractional part. How do we show the fractional part? Well, I don't know that. Except that those integer registers are supposed to be. Those general purpose registers are generally reserved for operations involving integers, although you can store float numbers there. Let's do a set R14, set R14 equal to 25. And that's wrong. Okay. $sign. And it looks like that. And now P/D $sign R14. It says you have a 25 in there. And everything works nicely with integers inside of the R-type registers. We want to see it in hex form, P/X $sign, where's the $sign? R14. And that's okay. And set $sign R14 equal to 1,000,000. 1, 2, 3, 4, 5, 6, 7, 8, 9. And P/D $sign R14. I think it's still 1,000,000. Okay, those are, let's see, what's left? We have to set the value of an XMM register. So first, let's view what's there. Then we'll change the value, and then we check it. So print /x $sign XMM0 dot. But then XMM0 has two halves. It has a 64-bit lower, a 64-bit upper half. We should specify which one. V2. So this is splitting it in two halves. V2, and we're looking for integers. 64 square brackets. Now the lowest is called 0, and the highest is called, well, in this case, 1. So, okay, it says we have this number, and it looks pretty bad. Let's see, could we display this as a float number? Let's take the same thing and change the formatting to float. Okay, and it's got some really ugly thing that's tiny number close to 0 because it's times 10 to the negative 130. All right, so let's change the value there. Set $XMM0, if I can spell that, M0 equal to something nice to work with. 4.75. Invalid cast. Now, why is that? Oh, there's a fix for it, but I don't remember it. We'll have to do something else. How did I set? Well, I forgot how I. Something for me to look up. I'm making a note so I have it. XMM0 equals 3.74. Well, I don't know. So let's try. There's some qualifier, I'm sure, that goes in front of that value. Oh, no. I got it. But $sign XMM0 dot. Remember, there's two numbers in XMM0. It doesn't know which one to put this 4.75. So let's say V2 underscore double. And let's choose, just for fun, choose the second of the two, equals 4.75. Excuse me, that didn't get the dot in there. Dot 75. Okay. Now we should have a number in there. So let's look at it. P/F, all that stuff again. $sign XMM0 dot V2 underscore double square brackets 1 brackets. That worked. Okay. Okay, so how can we get it in hex form? I think it should be just simply switch this to X. No, truncated. I think I know the answer. It's truncating the float number into just the leading integer, because hex form sort of goes compatible with treating bits as integers. That's the nature of being in hex, is it thinks those bits are all organized for an integer. If you wanted to see the hex version, we have to take away this double and put in its place int 64 bits. And is that 4.75? I think it is, because look, 401 is a known value to be 4. And 3 means is a little bit larger than the known value. And so Yeah, that's believable. It's 4.75. Okay, so how, which one we did X? Oh, can we assign a value there? I'm going to take, here, watch this. P, set, set, $sign X M M M 0 dot V2 underscore, and I'm going to assign to it a hex number. So I'll stick with integer 64 in one position equals, okay, so let's take this same, where can I get a hold of it? Copy that one, Control C, and paste it here, Control V. And just to be different, let's change the 3 to a 4. Yeah. And then say yes. And now what did we actually get? P/X $sign XMM0 dot V2 V2 underscore INT 64 brackets 1 brackets. Yeah, that's okay. How about in decimal? Oh, that treats it as a big integer, doesn't it? That's not the way to go. I wanted to see it in a floating point decimal number. So put an F here and change this to double. Oh, we lost the dot place. How do we get the fractions? I can't think of it. Fraction part. That should have done it. We should have seen something like 4.8, 4.9, somewhere in that area, not this rounded off fraction. P/F. Okay, I don't know the answer yet. 4, unless that's really a 5.0. I don't know. So let's do set $sign XMM0 dot V2 equal underscore. And I'm going to assign an integer to it. INT 64. Let's go to 0 here, equals 8. Okay, can we prove it? P/D $sign, that same thing, XMM0 dot V2 underscore INT 64 square bracket 0. Yeah, that's okay. Not all of them work, but I thought for sure I could actually output the new number. The old one was 4.75. We could easily output that one. But when I put this one in, and then I want to see it under the same circumstances, V2 double 1 X/F V21, we got a single integer. I can't quite explain it. Here I got my last shot at this. Okay, I'm going to take, copy it to here. Copy and paste it here. Okay, and then we're going to assign to it equals, let's make up a brand new number, 0x 402 C. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Now I want to view that the same way I was able to view X, this one. So if I can copy that, Control C. Let's see if we can view this same number. Control V. And it's number one. I think it's the same. We should get a floating point number on this. Got an integer. I can't explain it. I'll have to search for it, the answer this weekend. But here's the prototype. It worked here. P/F $B double one. And I just had put in 4.75, but I didn't like it here. Okay, I want to have a conclusion. What if you took all the bits in XMM0? That's 64 plus 64 for a total of 128. And then you said, I want to look at a 128-bit number, P/D, $, XMM0, and then you tell it the unsigned integer of 128 bits. And there's the integer. That's pretty big. This requires 128 bits to look at it. Could we do this in hex values? X, and we'll go here. Well, it's pretty big. That's more than 16 hex digits. That's in the neighborhood of 30 hex digits. It ends in an 8. I don't know how to explain that, except, but it's okay. Man, that's a big mantissa. And we'll leave it there. How about in binary? T. I see. It's mostly zero filled. There's a few bits that are ones in here, and there's that 8 at the end. That's a 1. But it's mostly zeros in that. If you treat those two registers as one big register. Okay, class, that's kind of the end of the GDB discussion. We're supposed to have 3 weeks left this semester. It's supposed to be a program where you use GDB. It's not solving anything difficult. It's like finding the area of a triangle, but there'll be places in the description of the problem where you're supposed to insert GDB commands, and that's practice in using it. Got any questions, people? Well, okay. Have a nice afternoon. I'm going to hang out here until 4 o'clock, but you should go program or work on some kind of classwork. And then we'll come back on next Tuesday. Okay. Have a nice Thursday. And I'm going to